This is a basic motor demonstration. We're going to use a coil of copper enameled wire. The enamel is an insulator. We have two wires that we're going to use to suspend the coil. We have a magnet, and this is going to be used for the static magnetic field. And we're going to use a power supply, but you can do this also with a 1.5 volt flashlight battery. To construct the coil, I used 24 or 22 gauge enameled wire, and this is just a number of turns that were actually wrapped around a D-cell flashlight battery to form the core. The battery was removed, then the ends were wrapped around the coil at each end. This is just to form two axles. I prepared the copper coil by removing the insulation all the way around on one side of this, where the axle is going to be. The other side was prepared by removing the insulation from just one side. So one side has bare copper and the other side has insulation. The copper loop is going to rest on the two wires, and you want to try to make sure you get this fairly well balanced. It doesn't have to be perfect, but getting a balance on here will help this turn a little bit smoother. Right now that's a little bit on the bottom heavy. And where you get this where you want it, then a couple of drops of super glue on the coils will help keep it there while you're experimenting. We're going to start with a 1.5 volt DC and place the coil on. What will happen with the coil is each time the coil rotates, the side that has half insulation and half bare copper is going to turn the circuit on and off, on and off. It'll do this fairly rapidly as it starts to spin, and this also then turns the magnetic field on and off. Right now we won't see any continuous rotation because we're missing one thing, and that's the static magnetic field for the coil to work against. I'm going to move the magnet into position, and we see that the motor starts to run. This coil will continue to operate as long as we have the magnetic field present by keeping the power turned on, or as long as the magnet isn't present. If we remove the magnet, the rotations will eventually stop. So what's happening is the coil is generating a magnetic field, and it has a north and south pole just like normal magnets do. And when we put this magnet in place, of course, the opposites are going to repel each other, like are going to attract. So as we move through here, this is very rapidly turning on and off as this axle rotates in this holder. And you can see we're getting a very, very fast rotation. One of the things that affects the power in the motor is how close the magnet is to the coil. As the magnet is moved away, eventually there won't be enough power in the motor to overcome the mass of the coil itself, and the rotations will stop. So as I move this away, we're going to see less and less power going into the motor, and it won't have enough power to keep rotation, so it's going to stop. I can move it back into the area where it should be able to rotate, but in this point it's probably not got enough power for it to start itself. But with a little bit of assistance, you'll see the rotations begin again. As I move the magnet in closer, there's more power in the motor, and it's able to rotate faster. There's another factor we can use to change the power of the motor, and that's the voltage being applied. As the voltage across the coil increases, then the power of the magnetism in the coil also increases. I've increased the voltage to 6 volts. It's still only generating a magnetic field when the uninsulated side of this axle is making contact with the metal support. As I move the magnet in closer, we'll see that the rotations will start increasing. Okay, I've got the magnet now in a close proximity, and you can see the rotations are extremely high. One of the things that we're starting to see now is that the axle is starting to jump out of the holder. When it's not able to make connection, it actually is slowing down slightly. So this is basically how the electric motors work that use a static magnet and a coil winding, a copper coil winding, to operate. This is about a half a volt applied to the coil, and that is only applied half the time. So when the axle that has the insulation removed is making contact, then we have power applied to it. Now I'm slowly increasing the voltage, which is going to increase the strength of the magnetic field in the coil. And as that strength increases, we're going to see more power coming from the motor, and it'll start to speed up in rotations. I'm now up to almost a volt being applied to the motor, and there's a significant increase in rotation. Now we're at about a volt and a half. This is a flashlight battery, so you can get this much rotation just by applying a flashlight battery to the circuit. As I move the magnet away from the coil, we'll start losing the rotations. So the proximity of the magnet to the coil is also a factor in being able to generate power from the motor. Many of the motors today use a magnet that is very, very strong for its size, and the reason that they do that is they can make the motor smaller but still have a lot of power in it. So strong magnets is going to be equal to having a lot of power in your motor. One other thing that we can do to increase the power of this motor is change the number of turns of wire in this loop. For each turn of wire, we get an additional increase in magnetic field as we increase the voltage across this magnetic field. If we take loop turns off, the magnetic field will get weaker. So if I wanted to increase the power of this particular motor, but I wanted to keep a constant voltage, let's say 1.5 volts, and I have a fixed value of a magnet, this particular magnet, but I want to increase the power of it, then I could increase the number of turns in this particular coil, and that will increase the magnetic field. This is the same thing as taking a wire and wrapping it around a nail to create an electromagnet. The more turns of wire you can put around the nail, the stronger the magnet is going to be.